Welcome back, everyone. Now we're going to do a little bit of an investigation. Yay. So, here we go. What happens when the mass of two objects change? This is starting to feel familiar, but that's okay. We're going to look at it again. We like our giants with their two objects, okay? And remember, if I look at them as they stand, I have a mass of force of 33,4. If I double the mass of mass 1, we realize that the force also doubles. If I double the mass of mass 2, no, that would make it 8. Now my total force compared to when I started is now 4 times bigger because force is directly proportional to mass 1 times mass 2. Both have to go together. So far, nothing new. We could use this to get some values, which we're not going to worry about. But what I need to look at now is we need to look at the relationship between mass and force as a graph. So we could use a simulation like that, where we take the mass and we take the force and then we plot it onto a graph. The important thing is we don't plot the masses separately. What the graph will look like is this. So we're going to have force on the y-axis because force is my dependent variable. Force depends on the masses. The masses don't depend on the force. So force goes on the y-axis. On the x-axis, we have mass 1 times mass 2. We now need to think about the units. Mass is measured in kilograms, but I have mass times mass, so it's actually kilograms squared. We would then get information, and now we plot it on the graph. When we do this as an experiment, all your points don't always fit nicely on the graph. So we draw a line of best fit. This line goes through the origin. It gets drawn like that, straight line. The fact that it goes through the origin is very important. Why do I know it goes through the origin? Well, if my objects have no mass, which isn't physically possible, but if they have no mass, they can have no force of attraction. It's as simple as that. So going through the origin works. This graph confirms for me that force is directly proportional to the product of the masses. This graph is a visual representation of the relationship. So from here, I can go force directly proportional to mass 1 times mass 2. If my graph does not go through the origin, then it's not directly proportional. So it can still be a straight line, but it must go through the origin. You have to keep that in the back of your mind because any relationship in science, if we say they're directly proportional, I must get a straight line and it must go through the origin. Okay? Let's look again at what happens when we change the distance between the objects. Let's reset these to what we had, and let's increase the distance. So if I go to 8 kilometers, let's go, we'll just put this, let's see if I can get him all the way there. Okay, he doesn't want to go any further, so let's take him to 8. I've doubled the distance. But that force is now 4 times smaller. So we realize that as the distance gets bigger, the force gets smaller. If I make the distance smaller, the force gets bigger. Okay, so I halved it this time. Halving the distance, so 2 times smaller, made the force 4 times bigger. So this is a square relationship. How do we put that onto a graph? So, if we look at it as a graph, what we would normally do is we go, this is r squared, which would be meters squared now. This is force in newtons. When we plot this graph, we get a curve. We get an exponential graph because we have the square. And we know that the further apart they get, the smaller the force. So my graph does this. At this point, you now all go, oh, it means they're inversely proportional. No, it doesn't. We have to prove the inverse proportionality. How do we do that? We have to draw a second graph. So we have to do another set of calculations. We have to work out the inverse of r squared. My graph now becomes a second graph. Force doesn't change. But now I plot a graph of 1 over r squared. If this is an inverse proportionality, I will now draw a graph that's a straight line through the origin. It will now do this, and it has to go through the origin. What that is telling me is that force is then directly proportional to the inverse of r squared. And how do we say that? Force is inversely proportional to r squared. So be careful here. You're going to be very tempted when you get this graph to go, it's inversely proportional. Not necessarily. You have to prove it. We prove it by drawing the second graph where we take the 1 over whatever that value is. And this goes across all your science. It's not just for this section. Very, very important. Please be careful with this one because I see it often. We started by asking about orbits. So, what happens when planets orbit the sun? So, let's see what happens when planets orbit the sun. Ooh, this is fun. I like this. So, here we go. We have that yellow dot is the sun. Over on the right-hand side, we've got the Earth. What I want to see is I'm going to show you the gravitational force, and you can see Earth and the sun attracted to each other. The size of the arrows are the same because it's the same force of attraction. And I'm going to show you, as it goes round, the path that the Earth travels. So let's let the Earth go around the sun. So there we go. We all know it travels at a nice orbit. Of course, the issue is why does it not go towards the sun? Because there's all sorts of other forces around it. And this we all know, and you can see we've almost done a whole year, because remember our years are 365 days. So when we get here, and we've almost done a year, so let's do a year, and okay, it's just over a year, it doesn't matter. But we know that around the Earth we have our moon. If we look at just the Earth and the moon, so there we go, Earth and our moon, same forces of attraction, has to be the same, Newton's third law. When I do that, oh look, it goes quickly. It's got a much smaller orbit it seems to be traveling quite quickly because it has a very short cycle. But that makes sense. Let's see what happens when I have the Earth and the Moon together. Now, the Earth's orbit's going to be a white line. The Moon's orbit's going to be pink. Watch here. Now you look at that and you go, hang on, something's gone wrong. But it hasn't. If we zoom in a little bit, so there's my Moon at the top, okay? So that's as good as I'm going to get. I want you to look at the Moon very, very carefully. Even though it looks like it's hopping, it actually is still going all the way around the Earth. It's because of the way it's moving. So watch, if you look carefully, you can see the Moon is going all the way around the Earth. So if we make it slow, if we look at it slowed down, you can see it goes all the way around the Earth still. The path looks like a nice, pretty flower because it's in relation to the sun. Now, the sun is attracted to both the Moon and the Earth. And that attraction changes size depending on where the Moon is. And the Earth is attracted to the Moon and the sun. And in fact, because of the interaction, because of those, that's why planets usually have an elliptical. It's not a perfect circle. They go around the sun in sort of like an egg shape because it's the interaction between all the other planets in the universe around it. But I find this actually very interesting. If we now look at a satellite, there we go. That's a geosynchronous satellite. It's a satellite that goes around the Earth in a complete circle. Where this satellite must be put is actually really important. It's not random. So they have to calculate how heavy is the satellite, how far above the Earth do we want it, because if, say for example, we make the satellite too heavy, we're going to make it heavy. Watch what's going to happen. So I'm going to let it go again. It's going to, okay, so far we're doing okay. It's still keeping on let's make it a bit heavier. Ooh, we're good. Okay, so we haven't got a satellite that's too big. But what if the Earth was bigger? Oh dear. Satellite went, pfft, maybe not, exploded, because it hit the Earth, or the planet that we're on, okay? If I make the planet, let's just reset it, so let's make the planet much lighter. Watch what's going to happen to the satellite. It's going to fly away. It might come back a little bit, but its orbit becomes very big, okay? Because now there's a very small force of attraction. This is not good for us because it's quite weird. Watch what happens here. We're going to do something because we can. We're going to turn the Earth's gravity off. Watch. So I'm going to let it go. Turn off gravity and off it goes in a straight line. We can't turn off the Earth's gravity. So, quickly, acceleration due to gravity. We know Fg equals mg. We know that F equals g m1 m2 over r squared. m1 and m are the same thing. Fg and F are the same. It's the force of attraction between two objects. So, mg is g, mass of my object. M2 is the mass of my planet divided by the radius of the planet. M disappears, so G is G M over R squared, where that's the mass of the planet. Mass of the object is irrelevant, and that's a good place to stop. That's all for now. We're going to take a short break, and we'll see you in a couple of minutes.